So we know from previous videos, if we were asked to anti-differentiate or integrate x squared with respect to the variable x, then I would just add 1 to the power, divide by the new power, plus c. But what happens now if I have a number up the top and the bottom of my integral sign? Well, this now becomes a definite integral. So for example, it might be that we need to integrate from 0 to 2 x squared with respect to the variable x. So what we do is first we integrate this thing, which we saw above, that this is just x cubed divided by 3 plus c. And we do this from 0 to 2. Now the next step is that I substitute my 2, I substitute my bounds into this equation. So I put my 2 in first. So if I put my 2 in, I get 2 cubed over 3 plus c. And then I'll subtract what happens when I put my lower bound in. So if I put a 0 in, I would get 0 cubed over 3 plus c. And now if we evaluate this, I end up with, well, 8 over 3 plus c here, subtract 0 over 3, subtract c. Don't forget to expand this bracket into this negative into both terms. So I just end up with 8 over 3. In fact, my c's, they actually cancel out. So a really cool trick that we've got here is when I put this, when I anti-differentiate and I pop it in here, I actually don't need this plus c because it cancels out anyway. Let's take a look at another example. So it might be that we need to integrate from 1 to 3, and we need to integrate 2x with respect to the variable x. Well, I integrate this thing, so I add 1 to the power, 2x squared, divide by the new power, which is 2, and I do this from 1 to 3. Well, just quickly, 2x squared divided by 2, that's just x squared, so I'm just left with x squared from 1 to 3. Now, I don't need my plus c because we just saw before that it cancels out anyway, so it doesn't really matter. Now, if I substitute my 3 in, so my upper bound first, I get 3 squared. And then I need to subtract my lower bound. When I put my lower bound in, I get 1 squared. So I just end up here with 9 minus 1, which is just 8. Another example, we'll just go through a few more. Let's integrate from minus 1 to 4, and we're going to do 3x squared plus 4x plus 1. Well, again, I integrate this thing, or I anti-differentiate it, so I get 3x cubed over 3 plus 4x squared over 2 plus x. And I don't need my plus c because it's going to cancel out, and I do this from minus 1 to 4. Well, if I just simplify that integral first, so I'm just left with x cubed plus 2x squared plus x. Now I substitute in my upper bound, so my 4. So I end up with 4 cubed plus 2 lots of 4 squared plus 4. And I subtract what happens when I put my lower bound in. So I get minus 1 cubed plus 2 lots of minus 1 squared. And we'll come over here, give ourselves a little bit more room, plus minus 1. Okay, so just some number crunching now. So 4 cubed, that's 64, plus I get 32 in there, plus another 4. So I end up with 100. Subtract. Now here I end up with minus 1, plus 2, subtract 1. So I just end up with 0. So I just end up with 100 as my answer here. So this answer evaluates to 100. If we do another one, so let's say that we were asked to integrate from pi on 2 to pi the cosine of x with respect to the variable x. Well, remember, first I just anti-differentiate that cosine of x. So if I do that, I just get sine of x. So we can pop that in. And I need to do this from pi on 2, this is in radians, up to pi. So I put in my upper limit being pi, so that goes in. And then I subtract what happens when I put my lower limit in, my pi on 2. And well, sine of pi, that's just 0, and sine of pi on 2 is just 1. So I get 0 minus 1, which is minus 1. We'll do one more example. Let's say we're asked to integrate from minus 2 to 3 e to the power of 2x with respect to x. So we're doing an exponential function this time. Well, again, I just integrate e to the power of 2x, and if I do that, I get a half times e to the power of 2x. Now, I don't need my plus c because, again, they cancel out, and I do this from minus 2 to 3. Well, if I do this from my upper bound first, so I end up with a half times e to the power of 2 lots of 3, which is just 6, subtract a half times e to the power of 2 lots of minus 2, which is just minus 4. So I end up here with a half outside of e to the power of 6, subtract e to the power of minus 4. And well, this is equal to, if you wanted to evaluate this as a decimal, 201.7. Now we could push this a little bit further algebraically if we wanted to. So we can write this as e to the power of 6 over 2, subtract 1 over 2e to the power of 4. So I'm just expanding this half in, and I'm writing e to the minus 4 as just 1 over e to the power of 4. And well, if we cross multiply this, I end up with 2e to the power of 10. So I'm cross multiplying up here, and then I cross multiply here. So subtract 2, all divided by, I then multiply my denominators, and I get 4e to the power of 4. And then I see I can cancel out a common factor of 2, and I just end up with e to the power of 10 subtract 1 over 2e to the power of 4. So that's it there, all in positive indices, which is always a nicer way to write things than what we have up here with negative indices. So that's it for these definite integrals. It's kind of just that pattern, and you do plenty of questions over and over again, and you'll start to get the hang of it really quickly. Now, this is going to become quite useful for us in application in a couple of videos' time, where we come to look at solving for the area under curves, and we're going to use these definite integrals quite a lot.